Hello friends, today we will start with the new topic on strengthening mechanism. As I told you when we were discussing plastic deformation, that this is one of the motive of our understanding of how the crystal deform, okay, so that I can design or tailor microstructure, or if I can do something in the material by which I can increase the strength of the material. Okay. Basically, I want to alter the properties of the material, okay, and all this understanding helps me to do that. Okay. So, we will start with the strengthening mechanism. Okay. So, there will be different strengthening mechanisms which we are going to discuss. So, my objective when I want to define when I want to discuss strengthening mechanism is to increase the strength of the material. That is my objective. Now, there can be two strategies to do that. First is remove all the defects from the material. Okay. If you remember, we discussed that the strength of the material, theoretical strength, okay, shear strength for example of the material is shear modulus divided by some constant here 2 pi. Now, shear modulus is in gigapascal. So, if you divide it by 2 pi also, order of magnitude will almost remain same, it will be in gigapascal, whereas all our experimental strength, shear strength is in megapascal. So, there is a 3 order of magnitude difference between what is theoretically calculated and what you have found out experimentally. And we said that there are some defects in the material which is bringing down the strength, and these defects we call as dislocations. So, first strategy is obviously for me is to remove all these defects, because these defects are bringing down the strength of the material, okay, which is of course not a easy task to do, okay, when you are talking about bulk material, because during the processing itself you generate so many defects. In some material people have achieved this kind of condition which are called whiskers. Okay. So, the idea for whiskers is that you make the dimension of the material so small, okay, suppose the mean free distance between two defects, okay, is in some micron, let us say 10 micron or 20 micron or so. Okay. So, one dislocation and another dislocation, there is this much distance is there, or one point defect to next point defect, some distance will be there, maybe in micron, 5 micron, 1 micron, whatever. So, if I make my dimension of one of the dimension of the material in that range, okay. So, let us say I make a material whose diameter, or make a wire which has a diameter equal to around 1 micron, let us say, then my dimension is lower than the mean free distance of the defects. Okay. So, I am practically eliminating all the defects from the material. Okay. Of course, I have to go to that kind of length scale to do that, and this is done in some type of materials which are called whiskers, which are very fine basically wires, and then you combine them together, and in those material where we could achieve no defect kind of condition, when people did experiment and found out the strength, they were in the range of gigapascal. Okay. So, basically defects are the main reason to bring down the strength. Now, this is a very expensive business to do all these things. Another way to do is this is second strategy is that I introduce too many defects. If I am not able to remove them, let us introduce large number of defects in the material, okay, so that they can start interacting with each other, okay, they will start cutting down each other kind of, and that will increase the strength. Okay. So, all the strengthening mechanism is based on this second strategy, that increase the number of defects, let them interact with each other, okay, and thereby you can increase the strength of the material. So, we know that the strength is intimately related to dislocation motion. Okay. So, at yield also what we say slip start taking place, the plastic deformation start taking place, and we know that slip takes place because of dislocation motion. Okay. So, strength is intimately related with dislocation. Similarly, UTS also if you see, we say that the material strengthened from yield stress to UTS because of strain hardening, and strain hardening is because dislocations are interacting with each other. Okay. So, again there is that dislocations are the main important unit you can say which decide the strength of the material. Okay. So, if I can hinder the motion of the dislocation by any mechanism, okay, then I am increasing the strength of the material. Okay. So, the idea for increasing the strength of material or strengthening mechanism to understand strengthening mechanism is to put obstacle in the path of dislocation movement. Okay. You put some barriers basically, and that is what you can see that all these cars have piled up because there is a barrier here, okay, and they are kind of getting piled up. And of course, you can see that the lead dislocation as they are piling up, okay, and then there will be a lot of stress on the lead dislocation, and there will also be a back stress on the other dislocation which are going to come. Okay. So, for example, a new car comes, it sees that there is so much pile up, maybe it will like to take some alternate route rather than standing in the line. Okay. Maybe some kacha road, if it is available close by, it will try to take that so that it can somehow get rid of this pile up. Similarly, the lead one, so the front car will see the kind of pressure of all the cars. So, if it is not able to the engine has stopped because of some reason, and it is not able to start, all the others will start honking. Okay. They will start putting pressure on the lead one. Okay. So, there is a back pressure and there is a stress concentration on the lead one also, okay, from all the dislocation which are behind it. Okay. And the other dislocation which are coming, they will see that there is a back pressure building up. Okay. So, by doing that, we are making it difficult for dislocation to move. So, when it sees so many dislocation, the next dislocation will find it difficult to move because there is a lot of back pressure build up, there is a lot of stress concentration because of all the dislocation which are in the queue. Okay. So, that is the strategy. So, dislocation pile up takes place at the barrier. Okay. So, barrier can be another dislocation. Okay. And if the barrier is another dislocation, and because of that if you are getting strengthening, then it is called work hardening. So, because of dislocation interaction. If the barrier is a grain boundary, then it will be called grain boundary strengthening. Okay. If barrier is precipitates, then it will be called precipitation hardening. If barrier is point defect, then it will be called solid solution hardening. Okay. So, we will see each one of them. Okay. I have grouped these three, actually these three are the ones which are you can call as strong obstacle. And this is actually a weak obstacle. So, these are strong obstacle, this is a weak obstacle. Actually, I can also divide them in different way, or I can group in different way. Okay. If you see these three, okay, the point defect and the precipitate and the dislocation, these three barrier come within the grain. So, they provide the barrier within the grain itself, whereas grain boundary provide the barrier at the boundary of the grain. Okay. So, you can make another group of these, okay, like this also, that this point defect, precipitation hardening, solid solution hardening and work hardening, they provide the barrier within the grain. Okay. So, you have a grain, let us say I am just making a hexagonal kind of grain. Okay. So, all these defects will be this 1, 2 and 3 will be within the grain, and the fourth one, the grain boundary strengthening, is only at the grain boundary. Okay. So, I can divide this into this way also. Now, my dislocation can also do can overcome this pile up, as I told you that if a car comes and it sees so many there is a pile up of cars, okay, or there is a queue of cars, it will try to take some other route. Okay. That is what dislocation can also do. For example, one of the mechanism is called dislocation climb. okay, which is dependent on the vacancy concentration in the material. Okay. So, for example, you have a dislocation like this. So, this is the extra half plane ending here and there is an obstacle here, and this dislocation want to move in this direction. Okay. What happens, there is a vacancy, for example, suppose there is a vacancy around here next to this obstacle. Okay. So, what will happen, this atom above this where the dislocation is ending, it has jumped into this vacancy, thereby creating a vacancy now at the where its earlier position was there, and the atom which is at the end of the dislocation core, that has now jumped up, okay, in the vacant position. Okay. So, thereby you have a dislocation climb now, okay, dislocation has climbed by one atomic distance. So, instead of ending here, now it is ending in this plane, and thereby it has circumvented this particular obstacle. So, now it can move in this plane without any problem. So, this is one way of circumventing the barrier by dislocation. Okay. So, it can also relieve the stresses at this location in the pile up by nucleating dislocation in adjacent grain or by nucleating a crack. So, these are other way of relieving the stress, or it can do a climb process to overcome the pile up. Now, as I told you that there are three mechanisms which are within the grain. So, let us start with the dislocation point defect interaction. Okay. That means, one of the method by which we have strengthening is called solid solution strengthening. So, it will come under point defect. Okay. So, you have point defects like vacancies or solute atoms. So, how they provide strengthening. Okay. So, these defects are associated with some strain field around them. Okay. For example, vacancies introduce tensile stress field around them. Okay. Substitutional solute atom create tensile strain field if the size is smaller than the solute. Okay. So, it will in that sense these two are going to be same. Okay. Whatever is the means by which vacancies introduce tensile stress, the same will be true for a substitutional solute atom having a smaller size. Then there can be a compressive strain field if the size is bigger than the solute atom. Okay. So, this is for substitutional solute atom. For interstitial atoms also this will be true. If the atom is having a larger size than the interstitial position, okay, and then it is going to put a strain on the nearby atoms, okay, and that will be a compressive stress. Okay. So, this will be true for an interstitial atom also whose size is bigger than the size of the interstitial site. So, you have different tensile and compressive field associated with different type of defects. We also know that dislocation also have a strain field. For example, in edge dislocation there is a compressive at the end of the extra half plane and tensile below it. Okay. So, I will just show you all the images for these three cases in the next slide. So, for example, if you look at the dislocation, so let us strain around dislocation. So, this is the edge dislocation ending here. So, you have compressive stress field on the top because you are introducing a extra half plane, okay, there, and there will be a tensile strain field in the bottom, okay, because now these bonds are stretched, you can see here, okay, all these bonds are stretched in a stretched condition, and there because of that there will be a tensile strain field around that. And similarly, because I am putting an extra half plane here, so all these atoms are going to be in compressive condition. Okay. So, there is a compression tension strain field associated with edge dislocation. With screw dislocation you do not get two different strain field, there is a spherical strain field or a circular strain field around the dislocation. Okay. So, in that case it will be different than what you are seeing in the edge dislocation. Now, if you look at the point defect, okay, suppose there is a vacancy or there is a solute atom which is of a smaller size, okay, what will happen, all these atoms which are next to the vacancies, they are in stretched position now. So, you can see the distance between the atom has increased, whereas distance between where it has not affected the atom, the distance is small, and here the distance is between the atom is more. So, all these atoms which are next to the this vacancies, they are in strained position, okay, and this strain is of tensile nature. If I put a bigger substitutional atom, okay, so this is for a vacancy or smaller solute atom. So, both cases. In this case you are going to get, so in this case I have tensile strain field, in this case I will have compressive strain field. Okay, so you can see that all the atoms are pushed very close to the next atoms. Of course, this will propagate, I am not able to show it, okay, I am just showing it for the next neighboring atoms. Okay, so this is actually the distance between the equilibrium distance between the two atoms supposed to be there. Now, the atoms which are next to this bigger atom, they are in compression. Okay. So, now this compressive field or this tensile field will interact with the tensile or compressive field of the dislocation. So, dislocation will feel very nice if it is if the tensile part is seeing the, for example, here the compressive part of the strain field around this particular atom. Okay. So, the tensile part will get cancelled out by the compressive part here, or if it sees this vacancy here, then the compressive part will be cancelled out by the tensile strain field of the. So, thereby dislocation will be able to reduce its strain energy. Okay. So, that is what it wants, to reduce its strain energy. Okay, and that is how they are going to interact, and that is how they are going to, the dislocation is going to see a kind of a barrier. So, it will like to be there because it is comfortable there. Okay. So, vacancies, like what will happen, that when you there is a dislocation, sometime vacancy will like to go and sit where the compressive strain field is there, okay, to the tensile strain field of the dislocation. Sorry, it will should be vacancy like at the compressive. Similarly, solute atoms, depending upon their size, like to accumulate around dislocation core. This atmosphere of point defects around dislocation put a drag force. Now, if I want to move dislocation now with these defects around the dislocation core, okay, my dislocation has reduced its strain energy, and if I want to move it, okay, so it would like to carry those defects with it, okay, and which this will create a drag force on the dislocation, okay, because now it is not only the movement of dislocation, the point defect also need to be moved together. If we increase the applied stress to a very large extent, maybe dislocation will be able to break free from these defects. Okay. So, that is also possible, that I apply a very large stress, this shear stress, and that will help the dislocation to break away from these defects. So, it gives rise to what this dislocation point defect interaction does, other than giving solid solution hardening, is that it gives rise to upper yield point, strain aging, and solid solution strengthening. Okay. So, all these three things are possible with this interaction between dislocation and point defects. So, if you look at the solid solution hardening, as I told you, dislocation will reduce its strain energy if these kind of defects are there around the core. Okay. So, you can see that there is a comparison. So, if I keep on increasing the nickel in a copper nickel system, if you remember when we were discussing copper nickel system, we said this is a isomorphous system. That means I can add any amount of copper, okay, and any amount of nickel to make an alloy, okay, because it is isomorphous system, there is no solubility limit. Okay. So, that is why you can see this is a nickel content is increasing. As nickel content is increasing, my tensile strength is increasing. Okay. Similarly, my yield strength is increasing. However, my ductility of the material is decreasing. Okay. So, if I increase the amount of nickel in this copper nickel alloys, okay, then my tensile strength and yield strength increases, ductility reduces. Okay. This is usually the case with all the strengthening mechanisms, most of them, that when you increase the tensile or yield strength, your ductility reduces. Okay. So, as I told you that why this solid solution hardening takes place is because of pinning of dislocation by strain field associated with the solute atom. Okay. So, between dislocation and solute atom the interaction is there, and that is helping you to increase the strength. As you can see, from 0 to 50% of nickel here, I am increasing the tensile strength from around maybe 225 megapascal to 400 megapascal or so. Okay. Similarly, yield strength I am increasing from around let us say this is this 50, 30, around 70 or 60 or 70 to around 160. So, a very big difference in the strength. Of course, the ductility is reducing from a value of 55 to around 30%. Okay. Now, if you remember when we were discussing tensile curves of steel and aluminum, I said in steel actually you get a very prominent yield point phenomena or very clear yield point you get. So, this is your elastic part, okay, linear part, then very sharp yield point, and after that there is a drop in the stress, and then there is some kind of you can see serrations are there. Okay. So, it is like this kind of serrations. This is what we call as yield elongation. Okay. And this is my upper yield point, this is my lower yield point, and after certain elongation then the strain hardening starts. Okay. So, this whole phenomena is called yield point elongation, yield point phenomena. Okay. And yield point elongation is that they show a localized heterogeneous transition from elastic to plastic deformation. Okay. So, why we are calling it as heterogeneous? Because it starts from one end and it goes to the another end. Okay. So, as you can see that the hedged region here is the location where the yielding has started, but in some of the portion of the material yielding has not started yet. So, it is starting from for example, some end here, and then it is propagating. So, you can see in the next stage somewhere here the yielding has increased up to this portion of the material, and this much is remaining the unyielded metal. And the third stage, if you can see, the most of the material has yielded, still some portion has left. Okay. And then at the end, of course, the whole material will be yielded. So, you can see that this is a heterogeneous transition from elastic to plastic deformation. Okay. It is not uniform deformation throughout the sample, as we said that deformation is going to be uniform throughout the sample. And this banding which you see here, two bands are moving towards each other, these are called Luder's bands. Okay. Scientists gave the name, first discovered them. So, on his behalf it is named like this. So, if you want to see that what this yield point phenomena is, the load after the upper yield point suddenly drop to approximately a constant value lower yield point and then rises with further strain. The elongation which occurs at constant load is called yield point elongation, which is heterogeneous deformation. Luder bands are formed at approximately 45 degree to the tensile axis during yield point elongation and propagate over the specimen. So, again 45 degree is coming back here. Okay. And why 45 degree? Again you have maximum shear stress acting in that direction to the principal stress, that is our tensile stress. Okay. And that is how the Luder band forms, and then it grows, and then it consumes the whole material. So, this is one way of yielding in plain carbon steel or low carbon steel, okay, which takes place. The upper yield point is associated with a small amount of interstitial or substitutional impurities. Now, why this yielding this type of phenomena takes place? Okay. The reason is that the solute atom, either carbon or nitrogen in low carbon steel, see that for any material, whether if it is annealed material also, dislocations are always going to be there in the material. Okay. So, to start with, the dislocation is going to be there in the material. Now, as I told you that the dislocation has a strain field and the solute atom also have a strain field. So, these atoms like to go and sit at the core of the dislocation depending upon what kind of strain fields are there. Okay. So, all the dislocations are already decorated, or there is a kind of atmosphere of these solute atom at the core of the dislocation. So, when we start the deformation process, okay, as I told you that there will be a kind of a locking of this dislocation because of this solute atom. So, if I keep on applying the stress on the material, okay, so you are forcing the dislocation to move, but these atoms are, the solute atoms are pinning the dislocation. But at some point you will have sufficient stress on the dislocation so that it starts moving, okay, and it will be pulled away from these solute atoms. Okay. So, where it starts breaking away from these atoms, that is my upper yield point. So, my stress is sufficient so that it is allowing the dislocation to get rid of this solute atom. So, as soon as they get rid of this solute atom, okay, they are free to move. So, suddenly there is a drop of the drop in the stress, because now they are free to move, okay, and then they are moving. Okay. So, the Luder band will start from two ends, then it will progress. So, that yield point elongation, at that time the whole material is getting consumed by the yielding process. Okay. And when the whole material is yielded, okay, now the dislocation has started moving in whole of the volume of the material, then the strain hardening part will start. Okay. So, it will raise the initial yield stress, this carbon and nitrogen, because of locking. When the dislocation is pulled free from the solute atom, slip can occur at lower stress. The magnitude of yield point depend on the interaction energy and concentration of solute atoms. The yield point phenomena has been observed in iron, titanium, molybdenum, cadmium and so on, zinc, aluminum alloys. Okay. In some aluminum alloys you will see yield point phenomena. So, the upper and lower yield point, okay, if you see this is an actual image of a Luder band formation, okay, in the steel, the source is also given here. So, you can see that how they are forming and they are going to progress over each other, and then they will consume the whole material. Now, the problem with this Luder band is that it affects the surface finish of the formed component. Okay. You can see that they are going to leave some this kind of stretch marks on the surface. Okay. So, suppose if you are doing a sheet metal forming, okay, you have a sheet which contains lot of dislocation, already carbon is there and it is sitting in the at the core of the dislocation, and you want to deform for making some car body, for example. And if this Luder band formation takes place, okay, it will affect the surface finish of the sheet. Because of the formation of this, you will see some kind of marks on that. Okay. And a customer, when he goes and he sees those marks, he will not like it. He will say that there is some defect in the material. Okay. So, this has prompted development of another class of steel called interstitial free steels. Okay. So, this is another type of steel. So, you get rid of all interstitial atoms, okay, so that you have an interstitial free steel, okay, and you can get rid of this Luder band formation if there are no solute atoms in the, or these interstitial atoms are there in the material. Okay. So, nowadays all the sheet forming you will see that these interstitial free steels are used, okay, and that is why now the painting jobs also become simpler. Earlier old automobiles, if you see, they used to put a putty over the sheet of the surface to make a very smooth finish on the surface, and then they used to paint it. Nowadays the painting is directly done over the sheet, okay, because all these problems are not there. Okay, another problem with solute atom and dislocation is called strain aging. Okay, so what do we mean by that? So, this phenomena in which the strength of a material increase with a loss in ductility after being heated at relatively low temperature after cold working. Okay, so what does it mean? For example, if you can see, this is a normal your elastic part, then upper yield point, lower yield point, yield point elongation, and then strain hardening. Okay. Suppose I stop the deformation at this point and I bring it back to the if I remove the load, for example. So, my load is removed, but this much strain will remain because this is the plastic part. And one more interesting thing, you can see that this is not going to be the strain in the material. Okay, I have shown the strain of the material by a slanted curve here. Okay. So, for any deformation process, there is always going to be some strain which is going to be recovered. So, this is my recovered strain and this is my permanent strain. Okay. So, this is permanent and this is recovered. So, whenever I will stop the deformation, okay, the total, it will not be this strain which I can plot get by drawing a perpendicular line to the strain axis. Okay, it will always be some strain which is going to be recovered, and this phenomena is called spring back. Just I forgot to tell you maybe earlier. Okay, that is why I am bringing it here now, that this much is strain is recovered, and this phenomena is called spring back. Why it is important is because when you are doing deformation and when you remove the load, some material, some deformation will be recovered. Okay, so if you are designing a part, okay, and suppose you have designed by the total strain, okay, so it after deformation its length should be this much, and this is going to be attached to another part. Okay, and this part is also going to be attached to another part, and this is what you wanted to have the strain in the material after deformation. So, suppose if you are taking the total strain, what will happen? There will be some recovery. So, you will find out after the deformation that the length of the part is smaller than what you wanted to attach. Okay, so what you have to do is, if you want this much strain in the material, always deform to a higher extent. Okay, so that you can get this much total strain. And how you can get this line? Actually, this line is parallel to the your elastic part, the linear part. Okay, so basically where you have stopped the deformation, from there you plot a line parallel to this linear elastic part. Okay, and wherever it is cutting this axis, and this will be your total strain. This much is recovered, this much is permanent. So, if I want this much as the total strain is permanent strain in the material, I have to have a higher total strain in the material, then I can have this much as the permanent deformation. Okay, this is something just a kind of a, I have rerouted something here. Anyway, so what we are doing here is, you have deformation upper yield point and then you started deforming okay, under the strain hardening part, and you have stopped the deformation here and you have removed the load. Okay. Now, you have after stopping, again you have loaded the sample and started deforming it. Okay. So, you can see that it has started from the same point where you have left, but if I stop this and keep the material at room temperature or maybe a little bit higher temperature for some time, what will happen is that you will see that there is again a reappearance of this yielding point phenomena. At this point it was not there, but if I after unloading at y point, suppose I keep it for some time and I allow aging to take place, okay, maybe artificial aging, room temperature aging, you will see that again the yield point phenomena has reappeared. Okay, and this is because you are giving time for carbon, nitrogen, these interstitial atoms to go and sit at the dislocation core. Okay. So, again now dislocation will have to come across these point defects to start the yielding phenomena. So, if I am not doing the aging, then you will not see this yield point phenomena, and it will start from where you have left. Strain aging should be eliminated. For example, in deep drawing steels, it leads to surface marking or stretcher strains. Okay. the amount of carbon nitrogen should be lowered by adding elements such as aluminum, vanadium and so on. Okay. So, these atoms will react or will form some kind of carbides and so on. So, there will not be interstitial atoms or carbon as interstitial atom, but it will form either aluminum nitride for example, with nitrogen, or titanium carbide with titanium and so on. So, they will form carbides and nitrides, and they will not be in free condition, okay, not in interstitial position. Okay. So, and this has to be removed because, for example, in deep drawing steel, as I told you, if you want to make a car body and so on, all these marks will be seen on the surface of the sheet. Then there is another problem called dynamic strain aging. Usually it happens at higher temperature. Okay. So, for example, you can see at room temperature there is no problem, you have a nice flow curve. At some intermediate temperature you start seeing that there is a serrations on the stress strain diagram. Okay. And these serrations are because of dynamic strain aging. Okay. So, this is basically repeated yielding due to high speed of diffusion of solute atoms to catch and lock dislocation. So, what is happening is, it is like a cat and mouse game between dislocation and the solute atoms. So, dislocation is moving, solute atom can also diffuse at high temperature. At room temperature, solute atom diffusivity will be very low. We have already seen in diffusion that diffusion depends on the temperature. So, as dislocation is moving, my atoms can also diffuse. Okay. So, if the velocity of dislocation and solute atom is kind of matching, then you will see that this cat and mouse game is going on between dislocation and the solute atom. At of course, very high temperature, the solute atom will be able to go diffuse with the dislocation. So, there is no problem. Okay. And the problem with dynamic strain aging is, it is not good for the ductility of the material. Okay. The ductility, where you see this dynamic strain aging, the ductility of the material comes down. Okay. And this effect of dynamic strain aging is called Potvin-Lee-Chatelier effect. Okay. So, with this I thank you. So, we have discussed the interaction between the point defects and the dislocations, and it can be used as a strengthening mechanism, as well as it kind of sometimes gives you problems which we have to understand to get rid of those problems. Okay. So, that is what we have understood. Okay. So, now next we will see another strengthening mechanism in the next lecture. Okay. So, thank you.